Hi everyone, this is Aruna, Assistant Professor, Department of Information Technology, SNS College of Technology. In my lecture series, today we're going to see about the closure of a set in functional dependency. So this is a very important topic under the functional dependencies. So because before watching this video, kindly watch my previous video. There I have given the detailed explanation about the Armstrong axioms and also what do you mean by functional dependencies, how we can calculate the valid and invalid functional dependency that is most needed while calculating the closure attribute. Let us see the definition of closure functional dependencies. Closure, it can be denoted by the symbol plus. So this is the how we can represent the closure. If plus represent over that is the closure attribute value for this particular attribute. So this is nothing but complete set of all possible attributes that can be functionally derived from the given functional dependencies. Through that particular attribute, we can able to determine set of all other attributes. Then only can we call it as a closure of functional dependencies. So how we can identify this thing? So that they given the functional dependencies along with by using the Armstrong rule or inference rule, we can able to calculate the closure set for the functional dependencies. For example, if F is a functional dependency, then closure attribute for that functional dependency is F plus. This is how we can able to represent the thing. So there is a 3-step for generating or for calculating the closure attribute. First, we have to add the attribute which is present on the left-hand side in the original functional dependencies. Second step is add the attribute present in the RHS of the functional dependencies. With the third step is with the help of attribute present on the RHS, check the attribute that can be derived from the other given functional dependency. Repeat this process until all possible attribute which can be derived from the functional dependencies. So these are the minimal steps for calculating the closure of that particular attribute. So first we have to present whatever the element present in the left hand side, that we're going to put it in the right hand side. So by using a right hand side attribute, if I can able to determine any value in the functional dependencies, then I have to put like that. So let us see along with the example. So before going for the example, so why we have to calculate the closure set means, so in a relation based on the primary attribute and non-prime attribute only, we can able to derive whether this is dependent or not. For that, we need the super key and the candidate key. Super key is nothing but the set of all attributes whose closure contain all attributes of given relation. Candidate key is collectively all the super keys are combined together, in which we're going to take the minimal set of an attribute. So that minimal set only we can call it as a candidate key. So this is a definition of super key and candidate key. Super key is defined as the set of all attributes whose closure contain all attributes of given relation. So the candidate key can be defined as a minimal set of attributes whose attribute closure is set of all attributes of the relation. So for example, consider a relation R of A, B, C, D, E having below mentioned functional dependency. My dependency 1 is A tends to B, dependency 2 is B tends to C, dependency 3 is C tends to D, dependency 4 is D tends to A. So first I'm going to calculate the A closure. So my first step is what are the components present in my first part, that I have to put it in my right hand side. So here it is A. So I have to put A over here. So by using A, I can able to identify the any other attributes or not, that I'm going to check along with this functional dependencies. By using A, I can able to identify B. So I can add B. So through B, is there any attribute I can able to identify? Yes, C. So if B can identify C means A also can able to identify C, because by using a transitivity property, we can able to identify the C. If C can identify D means by using a reflexivity property, A can determine the D. If D can determine E means definitely A also can determine the E by using a reflexivity property. By using union property, I can able to combine all my RHS part, that is A, B, C, D, E I can get if I take a closure. Similar how we have to calculate the B closure, C closure, D closure and E closure. And also combination of two. I have to calculate AB closure, AC closure, AD closure, AE closure. then BC closure, BD closure, DE, BE closure, CD, CE, then DE. This is the how the double 10 attribute closure can be calculated. Again, I have to calculate ABC closure. The next I have to get BCD closure, CDE closure, DEA closure, EBA closures. This is the how we can able to identify the closure set. So, and also in the particular regime, how I can able to identify all the possible super keys. How many super keys are present means here, this is a super key. Why I'm saying this is a super key? By using a, if I can able to identify all other attributes, because a table can contain only 5 attributes. Through that, I can able to identify all the attributes means then this particular relation is called as a super key. Similarly, this is also super key because by using a AD, I can able to identify all other attributes. But this is not a super key. Why I'm not saying this is not a super key means by using this attribute, I can able to identify only 3 attributes. A, B, I can't able to identify it over here. So this relation, it can be called it as is not a super key. So from this, we can have all combination of A, definitely it is a super key. So I can take, I can leave the A, remaining thing is B, C, D. So 2 to the power of 4 equal to 16. So there is a 16 possible keys can be present in this particular relation. So this combinationally, which one is a minimal subset? AD, it will have a is one proper subset, another D is another proper set. In this case, in this particular relation, A is a candidate key. Why I'm saying A is a candidate key means this is only a single set, single subset. So that only this particular relation, we can call it as a candidate key. So by using a closure only, we can able to identify the all possible super keys and the candidate keys present in the relation. Similarly, I'm giving 2 more examples. Through that, if you are calculating this thing, the same applicable. Here you are having a 2 functional dependencies. If I take a roll number closure, roll number, I have to put it in the right side. Through roll number, I can able to identify name and marks. That I have to put it over here. So through name, I can able to marks and location. Through name, I can able to marks and location. So by using a roll number, I can able to identify all others. So this can be a super key. This can be a super key. It is a single proper subset. So again, this can be the candidate key. So see through that, a relation can contain the n number of super keys as well as the n number of candidates. Why we have to calculate the super key and candidate key means if we want to fix a primary key for that particular table, that only depends only on the super key and the candidate key. Through that only we can able to identify them things. So this is the how we can calculate the closure of the attribute. Thank you. Thank you for watching my video.